Hi, so we are at section 3 now. Tracking changes in soil water storage and snow water equivalent in California. So we're going to look at plotting soil moisture anomalies and snow water equivalent anomalies. And this is going to be split in two sections. So section 3.1, which is going to load the GLDAS soil moisture images from an asset to an image collection. And then load GLDAS, literally do the same thing, but for snow water equivalent images. So really just looking at soil and snow. So for this part, the checkpoint copy and paste is a bit more complex. So I really recommend just following the book. It goes step by step with the code that you need to copy. But otherwise, your best bet is to copy what's in A2.1D checkpoint, because this will have everything that you require from this part. Because remember, what we just did was set the visualization parameters and have the linear trend based on TWSA. So really what you want is this part, because that is going to be section 3. So starting off, what is this section about? It is one of the most complex sections, I would say, but when we talk about GLDAS, we're talking about the Global Land Data Assimilation System that utilizes multiple land surface models to globally resolve fluxes and storage of water, which is what we're doing today, and energy at a 3-hour frequency. So an example of how to convert 3-hourly GLDAS snow water equivalent to annual for 2003 can be found in the additional script. At the bottom, it's the assignment 1. But this is just going to provide clarity on how the image assets were created for each GLDAS in this chapter. So this is just to get more details. But for this analysis, we're going to start with the script. We're going to import GLDAS for soil moisture and snow water. We're going to make estimates of soil moisture and snow water resolved at a 3-hour temporal frequency. And the time has already been taken to reduce the GLDAS data to annual means from the 3-hour estimates. Then we're going to aggregate monthly GRACE observations to annual average estimates to improve the efficiency of running this analysis. And if you feel as though you're more experienced or just have more confidence, you can adapt these methods to resolve monthly changes. However, it's important to note that if you're going to replicate the same methods for monthly rhythm, to interpolate the missing months of GRACE observations. So let's get into section 3.1. So first, section 3.1 is really going to be about loading the GLDAS soil moisture images from an asset to an image collection. So here we can see a bunch of assets being imported. When you copy and paste the code, it's going to look like this. All the SM is going to be the soil moisture, and all the SWE is going to be the snow water. First thing to do is really to convert so that you can import directly, and it's going to be at the top, up here. This is just going to make your life easier. Now let's go back to our code. Okay, so we want to load the soil water equivalent data to Earth Engine. So we're really just going to pick the SM data that we just imported, create a list out of it, and create a variable that is going to be an image collections from the images of the list we just created. Then we're going to convert the soil values to equivalent water depth units of centimeters, because before we compute these groundwater anomalies from GRACE and GLDAS data, we have to inspect the units to make sure that the math works, because if you remember correctly, we have an equation that we're going to be working with. And if we want the equation to work, we need the proper units. So what we'll do is in the search bar is that you're going to look at the image collection that we've just been talking about, and you're going to look into bands, and we're looking for soil moisture and snow water. Soil moisture is going to be under root moist. Okay, it's in kilogram by meter squared. And then SWE is kilogram by meter squared. So we need that in centimeters. Because if you recall, TWSA is in centimeters. So what this means is that you've defined the following conversion variable, but you need to map this over the image collection because you're working with a list here of data that you've collected for soil moisture. So what you do is basically, talked about in chapter 4 is map over an image collection. It's like running a loop. So you're going to apply the same function to each image and return the value back to the image collection. So this is what's happening here. You're simply converting and you're applying it to specifically soil moisture at the moment because that's what we're working with. Multiply it to do the conversion, rename it, and then you've got your conversion variable. Now, once we have this, we're able to plot the data to evaluate the soil moisture anomalies during the study period. So like a loop, when you look at here, this is what you're doing. So you're applying the function to each image and returning the value back to the image collection. And additionally, to converting the units, the code renames the variable and sets properties such as system time start, which is required in Earth Engine to plot data and compare it with other image collections, which is the next step we're doing. So you can decide what you want to print the variable as, either SMIC or SMIC-TS, right here. And this can just help to explore the differences between them. Now notice also that we've done a rename here. Instead of root moist ints, we've got SMA and we've got system time start. So it's just important to keep this in mind because when we plot the data to evaluate soil moisture anomalies during the study period, we got to understand what we're plotting. So here we're making a plot of soil moisture for the basin boundary because everything that we've done before leads up to this point. So we've got your color, you've got your format. We're basically creating the chart again as we did previously, but now we've got a lot more information that's about to come out. And you might notice if I run it right now, I'm just going to comment the rest out, that SMA is similar in magnitude to TWSA, but it's slightly out of phase with TWSA. So we're going to run it and compare. And this is going to appear in our console. This is going to be the same charts that we've been looking at here. So let's see what we get. It's running the layers below. Okay, so the soil moisture anomalies. As you remember, this is what we named our y-axis, and this is our timeline, and this is the SMA, so the soil moisture anomaly. So what's happening here? We can see there's a declining trend. So what we're seeing here is that there's a declining trend in soil moisture anomaly when you go from 2003, the fall, and 2006, again, fall, winter. So now let's look at snow. Quite literally the same thing as we just did, but for snow specifically. So again, the only thing that's changing is going to be your name for your chart and the list that you're creating for your image collection. But again, as we looked earlier, we're not in centimeters for this. So we have to rename our y-axis, set the time start, and basically create our loops so that all the conversions are applied to our images. And then we're going to visualize a new image collection. Without the previous step, it won't run. So you're going to plot the data to evaluate snow water anomalies during the study period, which in this case is 2003 to 2016, the same as the total water storage. And this is just, identifying the colors and the title. So we were saying earlier that the soil moisture was similar in magnitude, but a bit phased out. So now let's see what happens to the snow water. And in this case, we're going to see in our third chart, there is a big difference, as you can see. The snow water is much smaller in magnitude than the other two variables. These. Now, so then we're looking at these two graphs, and it's just giving us important information that we're going to need in section 4 and 5 just to resolve groundwater storage. Because we're also going to do surface water storage. But in this case, you can just start comparing when you're looking at the total water storage, the soil moisture anomalies, and the snow water equivalent anomalies. It's just helping you understand a bit more what's happening with this trend. And as you can see, there's a declining trend in soil moisture, and there's still a declining trend in snow water. But snow water is still much smaller in magnitude than the other two variables. Look at it here. If you compare this trend to this trend, if you look at the centimeters, there's quite a difference. Same as it goes here. So as we look at these differences and comparing these graphs, I want to add that when you're looking at these different graphs comparing the soil moisture, the snow water, remember that we have droughts. Two droughts that we're looking at, the 2006 to 2009 and the 2012 to 2017. So when you're looking at the graphs, you can see that with the snow water, it's somewhat stable. Usually, as we mentioned earlier, that's when there's the most water available because you've got the snowpacks, and the reservoirs are not being used. But then you've got the soil moisture, and you can really see that between these droughts is where these big declines are happening. So this is when the water is being used by these reservoirs, as we mentioned earlier when we were looking at these charts. And when we were looking at the declining trend on our map layers. This is what we're seeing here. So it's just something to keep in mind when you're looking at these graphs and what you're analyzing. So in areas, for example, of snow water where perhaps there's a big decline or something is happening, especially around the droughts, can be like we talked about in the darker areas where there's just a region not receiving enough winter rain or snow and having just the most junior and recent surface water rights. And then when you're looking at it in a more seasonal trend, the winter months, as I mentioned, are going to have the maximum water storage because of snowpack, full reservoirs, and so on. And then you're going to have summer and early fall, and this is forgetting the spring where everything's melting, where the red reservoir water has been used and the soil is drying out. So this is what we're seeing these really big droughts, and we're seeing the soil moisture going down. So by looking at these and comparing these, this is just giving you an idea of how we plot these changes, how we plot these anomalies, and how to create charts and how to map trends on layers and off layers, just such as in the console. So we'll keep going, section 4 in the next videos.